Hi, this is Praveen, Assistant Professor, Department of ECE, Sri Muthukumaran Institute of Technology. Today we are going to discuss about Unit 4 applications in the subject CEC365 Wireless Sensor Network Design. This unit focuses on application layer protocols used in wireless sensor networks and 6-LoWPAN environment. Unlike traditional IP networks, embedded and sensor networks operate under severe constraints such as low power, limited bandwidth, and small memory. Hence, application protocol design must be efficient and lightweight. This unit introduces design challenges, protocol paradigms, real-time communication, and widely used application protocols. Understanding these concepts is essential for developing scalable and reliable IoT systems. Design issues. Application protocol over 6-LoWPAN must consider constraints that are not significant in normal IP networks. These include limited package size, unreliable wireless links, known mobility and energy constraints. Protocols must be robust to packet loss and delays. Design choices directly impact battery life, latency, and scalability. Hence, careful protocol selection and optimization are crucial. These issues includes link layer issues, networking issues, host issues, compression issues, and security issues. First, we will discuss about the link layer issues. 6-LoWPAN operates over IEEE 802.2.15.4 radios, which have very small frame sizes and low data rates. These links are lossy, asymmetric, and affected by interference and fading. Multicast support is limited and retransmissions are restricted. Applications must therefore tolerate unreliable links and minimize packet size. Efficient encoding and reduced control overhead are essential. Next, we'll discuss about networking issues. UDP is commonly used in 6-LoWPAN due to its low overhead compared to TCP. However, UDP does not provide reliability, ordering, or congestion control. Application must implement these mechanisms if required. Fragmentation increases delay and packet loss, so protocol should use small payloads. TCP is generally unsuitable without major modifications. Next, host issues. Device identification is critical in embedded applications such as monitoring and automation. IPv6 addresses are not reliable identifiers because they change with mobility and network attachment. Stable identifiers like EY64 or serial numbers are preferred. Domain names are more application friendly since DNS can update IP address dynamically due to sleep schedules. Communications should be asynchronous. Compression issues. 6-LoWPAN has extremely small payload sizes, making compact application protocols essential. Many traditional protocols are verbose and text-based, such as HTTP and XML. Compression techniques like binary XML and EXI reduce message size and processing complexity. Compression can be implemented end-to-end or through proxies at the network edge. Designers must balance efficiency and complexity. Next, security issues. 6-LoWPAN primarily relies on IEEE 802.15.4 link layer security using AES encryption. However, this provides only hop-by-hop security and is vulnerable at intermediate nodes. Sensitive data requires end-to-end application layer security. Embedded devices have limited resource and cannot support complex firewalls. Edge routers must provide strong traffic filtering and protection. So with this, we have seen the design issues in application layer protocols. Next, we will move on to the protocol paradigms. So protocol paradigms define how devices communicate and exchange data. Common paradigms include request response, publish, subscribe, and event-driven models. In constrained networks, these paradigms must be lightweight and energy efficient. Publish, subscribe, and event-driven approaches reduce unnecessary communication. Selecting the right paradigm improves scalability and network lifetime. In which we will first discuss about end-to-end paradigm. So the end-to-end paradigm enables direct communication between application endpoints without intermediate processing. This model simplifies protocol design and supports efficient compression. In 6LoWPAN, end-to-end communication helps manage intermittent node availability. Compression can be implemented directly by application or transparently during proxies. This paradigm is important for maintaining data integrity. Next, we will move on to real-time streaming and sessions. Real-time applications such as sensor data streams, audio and video require timely delivery. IP provides best effort delivery, so packets may be delayed or lost. UDP is preferred because TCP retransmissions increase latency and jitter. Dropping outdated packets is often better than delaying data. Protocols like RTP and SIP manage streaming and sessions. Next is publish-subscribe paradigm. In this publish-subscribe model, senders publish data without knowing the receivers. Subscribers receives data based on topics or content. This paradigm decouples publishers and subscribers, improving scalability and flexibility. It reduces communication overhead and is well suited for IoT systems. MQTT and MQTTS are popular implementations of this model. The next is web service paradigm. Web service enables interoperable machine-to-machine communication over networks. They typically follow a client-server model using HTTP. Two major types are SOAP-based and REST-based services. SOAP. SOAP uses XML and WSDL, while REST uses lightweight URL-based access. REST is generally more suitable for constrained environments like 6LoWPAN. So next we will see about the common protocols. The common protocols that are commonly used or have good potential for use over 6LoWPAN. Several application protocols are suitable for 6LoWPAN networks. These includes web services, MQTTS, ZigBee, CAP, SNMP, RTP, SIP, and some industry-specific protocols. Each protocol addresses different application needs such as monitoring, control, streaming, or management. Choosing the correct protocol is critical for efficient and interoperability. So we will now see the protocols one by one. First, we will see about web service protocols. So web service protocols are widely used in enterprise systems but are heavy for low power networks. They rely on HTTP, TCP, and XML, which increase overhead. SOAP uses structural XML messages with headers and bodies. REST uses simpler source-based access with HTTP methods. REST-based services are more suitable for this embedded system applications. Next, we will move on to MQTTS protocol, which is nothing but message queue telemetry transport. This is a lightweight publish-subscribe protocol designed for use in enterprise applications over low bandwidth, wide area links such as ISDN or GSM. MQTT uses broker-based publish-subscribe architecture to which clients publish data based on matching topic names. MQTT is a lightweight protocol. MQTTS is an optimized version developed specifically for sensor networks. It operates over UDP and supports small devices with limited resources. So it is made up of 4 different elements: MQTT brokers, MQTTS gateway, MQTTS forwarders, and MQTTS clients. MQTTS reduces overhead while maintaining scalability and reliability. It is widely used in IoT applications. Its message structure consists of a length field, a message type field, and then a variable length message part. So MQTTS includes a gateway discovery procedure which does not exist in MQTT. Alternatively, clients can pre-configured with the gateway location to avoid discovery overhead. MQTT architecture includes clients, gateways, forwarders, and brokers, which we have which we have explained before. So clients connect to a gateway with respond with an acknowledgement. Disconnect is used to end an connection or to indicate a sleep period. Clients can connect with multiple gateways which are able to perform load balancing. Gates can function in either transparent mode or in aggregation mode. Next, ZigBee Compact Application Protocol. We'll simply call it as ZigBee CAP. ZigBee CAP enables ZigBee application profiles to run over UDP IP networks. Generally, the ZigBee application layer and the ZigBee cluster library specifies an application protocol enabling interoperability between ZigBee devices at the application layer. A solution for using ZigBee application protocols and profiles over UDP has been proposed in IT TollCap, which is an IETF internet draft. This specification defines how the ZAL is mapped to standard UDP IP primitives, enabling the use of any ZigBee profile over 6LoWPAN or standard IP stacks. This adaptation layer of ZAL for use with UDP is called the Compact Application Protocol, which we shortly call it as CAP. Next, we'll discuss about CAP protocol stack. CAP encapsulates ZigBee application messages, including UDP datagrams. It replaces IEEE 802.15.4 addressing with IP-based addressing. CAP supports security, acknowledgements, and discover mechanisms. APS delivery modes are mapped to IP unicast and broadcast. This allows seamless integration of ZigBee application over IP. Then SNMP. SNMP is a standard protocol for network management and monitoring. Network management is essential for all networks, including autonomous wireless embedded system. The expansion of SNMP is Simple Network Management Protocol. It consists of SNMP Manager, SNMP Agent, and Managing Information Base, which is shortly called as MIB. SNMP allows get and set operations to retrieve and configure device parameters. SNMP v3 provides enhanced security features. It is useful for managing embedded IP devices. Next is Real-Time Transport Protocol, RTP. RTP is used for transporting real-time data streams such as audio and video. It provides sequence numbering and timestamps to manage jitter and packet ordering. RTCP provides feedback on quality of service. SIP is used to establish, modify, and terminate multimedia sessions. These protocols are widely used in VoIP, voice over IP systems. That VoIP is the one which we are using in our mobile phones. Next, we'll move on to the industry-specific protocols. Industry-specific protocols are widely used in building automation and energy systems. These industries require interoperability across multiple vendors. Such protocols have evolved to support IP communication. Some protocols require compression or IPv6 support for 6LoWPAN. They enable large-scale enterprise deployment. So first among this industry-specific protocol is BACnet, which is nothing but Building Automation Control Network. It's an ISO and ANSI standard protocol designed for interoperability among building automation devices. It is used in HVAC, lightning, fire alarms, and security systems. BACnet uses collapsed to OSI model and supports multiple physical layers. BACnet IP enables direct communication over IP networks. It supports scalable and interoperable building managements. Advantages include scalability, vendor independence, flexibility, and widespread industry adoption. BACnet is used to integrate and control multiple building systems through a unified building management system, which is shortly called as BMS. The next protocol which you are going to see is KNX. CONEX is an open internationally standard protocol for home and building automation. It supports twisted pair, power line, RF and IP communication. KNX is widely adopted in Europe and supported by many manufacturers. KNXNet IP enables integration with IP networks. It supports large and scalable installations. KNX RF operates at 868 MHz with a data rate of 16 kbps and supports large data network. KNX networks can theoretically scale up to about 64,000 devices. Next one is OBIX, which is nothing but Open Building Information Exchange. It is a web service based standard for accessing building automation data. It provides a normalized XML representation of points, alarms, and histories. OBIX is extensible and protocol independent. It can operate over SOAP and REST with compression and UDP IP. It can be adapted for 6LoWPAN also. The next protocol is ANSI C12.19. ANSI C12 standards are used for smart metering in North America. C1219 defines standardized data tables for utility meters. C12.22 supports IP-based communication using compact binary encoding. Small frame sizes make it suitable for low bandwidth networks. It supports reliability and security features. Next one is DLMS slash COSEM. So DLMS COSEM is an IEC standard used mainly in Europe for utility metering. DLMS defines messaging while COSEM defines the object-oriented data model. It supports UDP and TCP over IP networks. The protocol can be adapted to IPv6. It is suitable for 6LoWPAN despite slighter large data formats. So today we have in this unit we have covered application design issues, protocol paradigms, real-time streaming, publish subscribe models, and web services. It also introduced key protocols such as MQTT, CAP, SNMP, RTP, SIP, and industry-specific standards. These topics form the foundation for IoT application design. These are essential for real-world deployment. So application protocols over 6LoWPAN must be lightweight, secure, and energy efficient. Protocol paradigms play a key role in reducing overhead and improving scalability. Protocols like MQTT, RTP, CAP, and industry standards enables diverse IoT applications. Proper protocol selection ensures reliable and efficient communication. So this concludes the discussion of Unit 4 applications. Understanding these applications helps in designing efficient wireless sensor and IoT systems. Thank you for your attention.